Hi, my name is Mohammed Rian bin Mohammed Rafi. Admin number 2402361F, and this is my MedELN project.
So first things first, I want to show you my circuit. Its main purpose is to amplify biosignals so that it can be readable and measured for medical procedures to happen. Biosignals are normally too small for the human eye or ear to sense, which is why it is needed to be amplified. My circuit specifically boosts heartbeat audio from the stethoscope acoustic output and processes it to the speaker, which will output an amplified version of the heartbeat. So looking over at the schematic of the circuit, there are 4 individual blocks that each serve their own purpose. We will go deep into detail about each block later. Firstly, the signal is passed through a closed-loop non-inverting operational amplifier, which as the name states amplifies the signal. It is then driven to another one, but this time it has a negative feedback loop and an adjustable using an adjustable trimmer potentiometer P1. Together, both stage 1 and 2 provides a high but controlled overall voltage gain. After that, it is led to an op-amp that's configured in a silent key second-order low-pass filter, which allows low frequency to pass through while blocking high frequencies. And finally, it is connected to an audio amplifier, which further boosts the signal for it to become measurable. So let's take a look at block 1 of the circuit. It revolves around the op-amp TL072 and as mentioned is a closed-loop non-inverting amplifier. The coupling capacitors C1 and C4 both blocks DC signal but allows AC signal to pass through. The non-inverting pin is connected to a voltage divider circuit with R5 and R6 both having values of 10K and Vin being 9 volts. That gives us 4.5 volts. It acts as a level shifter that prevents the sine wave from being distorted and is forced to single supply mode. The output is looped back into the inverting pin of the op-amp through capacitors C2, C1, C2, C3, and resistors R2 and R3. Together, the capacitors and resistors form a low-pass and high-pass filter connected in series, which results in a band-pass filter. By doing some calculations, I can conclude that the band-pass gain is 23 using the following formula. The table below shows the data I gathered for V out. I measured TP2 to get V out and tried different frequencies to see how it varies. Notice how the gain does not exceed 23 volts. That's because as we have calculated earlier, 23 volts is the maximum voltage gain. After that, it is converted to decibels. Next, I crafted a frequency response curve and sure enough, it showed a band pass frequency curve over here. The -3 decibels drop determines the cutoff frequency, and below is where I calculated the bandwidth. So the frequency cutoff is here. So I put another line all the way to the frequency below. This is for the low cutoff frequency, and this is the high cutoff frequency. This is where I wrote it down, and this is where I calculated the bandwidth, and the formula is high cutoff frequency minus low cutoff frequency, which is equals to 1485 Hz, 1485 Hz. So this is me measuring TP2, the output of the circuit. Over here is the graph, the sine wave on the oscilloscope with frequency 200 Hz, and the V peak to peak is 4.46 volts. Then afterwards, I changed the frequency to 1k Hz just to show how the output varies. So now the V peak to peak is 3.46 volts, approximately around there. The second block of the circuit shows us variable gain amplifier with a negative feedback. The voltage gain is adjustable through the trimmer potentiometer. As there is negative feedback, a part of the output voltage is reverted back into the inverting input of the op-amp with a 180-degree phase inversion. As you can see here, the same voltage divider circuit is used as we saw it in block 1. Since TL072 is a single supply op-amp, I need to bias the signal mid-rail so that the op-amp can amplify AC without clipping to 0 volts. As shown here, this is the one that is desired, a clear sine wave like this. Not this, because this is clipped at the 0 voltage here. Since it is a non-inverting amplifier, we use this formula to determine the gain. Assuming the trimmer is at its max resistance, this is the max possible gain we could get from this amplifier. This is me measuring my TP3 in my own circuit. So this is the waveform shown at the oscilloscope with a voltage peak to peak of 6.16 volts. This is me adjusting the trimmer potentiometer. And as you can see, at its max resistance, the waveform is clipped. So I had to adjust it so that the waveform is shown clearly and not clipped like earlier on. This is at 200 Hz. I adjust it to 1 kHz just to see how different frequencies affects the waveform. So over here I get voltage peak to peak 4.08 volts, and yeah, that's my measurement of TP3. The third block shows a Sallen-Key second order active low pass filter. This configuration is used to filter for certain range of frequencies. It allows only low frequencies to pass through, but not high frequencies, to isolate the important biological sounds and removing unwanted noise. How do I know it's a low pass filter? It's because of how the resistors and capacitors are arranged, with R8 being here and C6 being here. If it was the opposite position, it would be a high pass filter. Since there are two sets of capacitors and resistors, I can determine that it is a second order low pass filter with a slew rate of negative 40 decibels per decade. Speaking of the cutoff frequency, this is how we calculate it using this formula. As a result, I got 995.925 Hz as my cutoff frequency. These coupling capacitors are in charge of removing any DC offset from the previous block or from going to the next. This table below shows the output of the Sallen-Key second order low pass filter, and this is section of the V out, and notice when it comes to 1000 frequency, which is the approximate cutoff point for the low pass filter, it starts to attenuate. It starts rapidly going down in decibels also. So this is the graph I drew. This is the accurate depiction of a low pass filter for frequency response curve, and it is at negative 0.5. The negative 3 decibels drop point is here at negative 3.5, and I draw a line here which intercepts this part of the graph, and when I drew it all the way at the x-axis, sure enough it is 1000 Hz. So calculating the bandwidth, it's the cut-off frequency minus 0 for low pass filter. And remembering the calculations we made earlier on, which was 995 Hz, it is almost the same as what we got here. This is me measuring TP4, the output of block 3. So as you can see here, the sine wave labeled at the oscilloscope with a voltage peak to peak of 3.16 volts at 1 kHz. And since stage 2 is directly connected to stage 3, the trimmer potentiometer from the stage 2 would affect the output at TP4 as well. As you can see here when I was adjusting the trimmer potentiometer. But not least, we have the block 4, which shows an audio amplifier. LM386N-1 is a low voltage supply audio amplifier. Here, we have a coupling capacitor C13 that allows AC signal to pass through but not DC signals. We have C15 as the bypass capacitor, which main purpose is to reduce power supply noise and improve output stability. And lastly, we have P2, an adjustable potentiometer which controls the output volume of the whole circuit. This is me measuring TP5, the output of the whole circuit, and there we have the sine wave of the output TP5, peak to peak 5.76 volts around there with 200 Hz. And this is me adjusting the potentiometer at TP5 at block 4. As you can see, it gets clipped, so we have to choose a suitable resistance for the potentiometer. And as I adjusted the trimmer potentiometer, the voltage changed to 6.4 volts. So we know that it is directly responsible for adjusting the output volume of the whole circuit. This is me changing the frequency to 1 kHz. Now the V peak to peak is 1.86 volts.
So thank you very much. That is my medical electronics project. My name is Mohammed Rian bin Mohammed Rafi, admin number 2402361F, and thank you for your attention.